By extending the topic of kinetic theory, today we will study the kinetic theory of an ideal gases. So go for the topic name first. Under the kinetic theory of an ideal gas. The kinetic theory of a gases is based on the molecular picture of a matter basically. A given amount of gas is a collection of a large number of molecules. Typically, that is the Avogadro's number, that is 6.023 into 10 raised to the power 23, that are in incessant random motion. At ordinary pressure and temperature, the average distance between the molecules is a factor of 10 or more than the typical size of a molecule, that is 2 angstrom. Here 1 angstrom equals to 10 raised to the power minus 10 meter. Now, thus the interaction between the molecules is negligible and we can assume that they move freely in straight line according to the Newton's first law. However, occasionally they come close to each other and experience intermolecular forces and their velocities changes. These interactions are called collisions. So, how we can define collisions? The gas moving molecules or particles come close to each other, moving molecules come close to each other and they experience intermolecular forces and experiences the intermolecular forces and their velocities changes. These interactions are called are called collisions. Now the molecules collide incessantly. These molecules collide incessantly against each other or with the walls and change their velocities. The collisions are considered to be elastic. We can derive an expression for the pressure of a gas based on the kinetic theory. For this, we need to begin from the idea that molecules of a gas are in incessant random motion colliding against one another and with the walls of the container also. All collisions between molecules among themselves or between molecules and the walls are elastic. This simply implies that total kinetic energy is conserved and the total momentum is conserved also or as usual. Now come to the topic pressure of an ideal gas. For this, you need to consider a gas enclosed in a cube of side 1. We can draw a diagram for this. It will be something like that. Now here we can consider this x-axis as usual. This will be our y-axis and this will be definitely a. Now what happens? Suppose this is a colliding particle of a gas. It collides with this wall of this container and move like this. Okay. So the coordinates here of the velocity of this particle is Vx, Vy and Vz. And for here it becomes negative. So it must be minus Vx, Vy and Vz. Now what this figure shows? This figure shows the elastic collision of a gas molecule with the wall of a container. Elastic collision of a gas molecule with the wall of container. Now here we can write clearly that by consider a gas enclosed in a cube of side 1, take the axis of to be parallel to the sides of a cube as shown in the figure above. Now the molecule with velocity Vx, Vy, Vz hits the planar wall that is parallel to y-z plane of area. Here A is equal to L square. Okay, that will be area L by L. Since the collision is elastic, the molecule rebounds with the same velocity. Its y and z component of velocity do not change here in the collision, but the x component has a reverse sign because it is opposite to the x direction after the collision. So the velocity after collision is minus Vx, Vz and Vy. The change in momentum of the molecule is, we can show here, the momentum of molecule after collision, that is minus Vx. That will be negative after collision, and this will be initial, final, and this will be initial. Okay, so final minus initial will give you the change in momentum. Okay, so we can say that is del P, or here it will be minus ka 2 and Vx. Okay, now by the principle of conservation of momentum, the momentum imparted to the wall in the collision is 2 mvx. So by the principle of momentum conservation, the momentum imparted to the wall in the collision is 2 mvx. Now to calculate the force and pressure on the wall, we need to calculate the momentum imparted to the wall per unit time. In a small time interval del t, a molecule with x component of velocity vx will hit the wall if it is within the same distance vx del t from the wall. So we can write here, in order to calculate the force and pressure on the wall, we need to calculate the momentum imparted to the wall per unit time. This will all happen in a small time interval del t. In a small time interval, let us suppose del t, a molecule with x component of velocity vx will hit the wall if it is within the distance vx del t from the wall. A molecule with x component vx del t from the wall. That is, all molecules within the volume avx del t only can hit the wall in time del t. That means within the volume avx del t only can hit the wall in time del t. Can hit the wall del t. But on the average, half of these are moving towards the wall and the other half away from the wall. Now, thus the number of molecules with velocity vx vy vz hitting the wall in time del t is, so the number of molecules with velocities vx, vy and vz in del t time is half of a vx del t, and where n is the number of molecules per unit volume, where n is the number of molecules number of molecules per unit volume. Now the total momentum transferred to the wall by these molecules in del T is the total momentum transferred to the wall in del T time is something is Q equals to 2 mv. Q equals to 2 mvx will be half of L A Vx del T. This will be the equation 1. Here the force on the wall is the rate of momentum transfer Q upon del T, and pressure is force per unit area. So we can overwrite here that force on the wall is the rate of momentum transfer, Q upon del T, and pressure is force per unit area. So we can write P is equal to force upon per unit area. Here it will be N mvx square. This will be equation 2. Now actually all molecules in a gas do not have the same velocity. There is a disturbance in the velocities. Now the above equation therefore stands for pressure due to the group of molecules with speed Vx in the direction x, and N stands for the number of density of that group of molecules. Here we can write where N stands for number of density of that group. Number of density of that group of molecules. That group of molecules. That's it. Now we can write the total pressure is obtained by summing over the contribution due to the all groups. So we can perform summation here, which is P equals to nvx square. This will be equation 3, where Vx square bar is the average of Vx square. Average of Vx square. Now the gas is isotropic, that means there is no preferred direction of velocity of the molecules in the vessel. Therefore, by symmetry we can write Vx square bar equals to Vy square bar equals to Vz square bar. Here, what we have 1 by 3, because we are taking average over here, 1 by 3 so it will be 1 by 3, where V mu is the speed and mu square denotes the means of the squared speed. V is the speed and mu square denotes the mean of squared speed. So here we can write P is equal to half by 3 and V square. Okay, that's all for today. Thanks you.